This is the solutions video to assignment 8. Let's start with question 1. We are given a logic minimized Boolean function and asked to find out what the minimum possible Cmos stack size is in the implementation of f bar with equal rise and fall delay. So the hint is to check if f is self-dual. So let us do that. To first, an analysis of the expression of f says that if any three variables is equal to 1, for example, let's say a equal to b equal to c equal to 1, then this expression will become 1, and so therefore the entire sum will become 1, right? So the idea is that since you have four such possible, you have four variables and you have to choose 3. So therefore you have 4 such possible expressions and all 4 of them are included here, which means that if any 3 variables is equal to 1, then f is equal to 1 and f bar is equal to 0. So I have expanded the truth table for f, and similarly you can just replace 1 by 0, 0 by 1 and 1 by 0, you will get it for f bar. So let us now check if the function is self-dual. So the self-dual property is that f of x vector the whole complement is, f of x vector complement is, that is the bitwise complement of x vector, is equal to f complement of that vector. For example, if this row is one x vector, right, and if you take its bitwise complement, which is this row, then this is f of x vector, this is f of x vector complement, which is equal to 1, this is equal to 0, and clearly you can see that f of x vector complement is equal to 1, which is equal to 0 complement, which is equal to f of x vector complement, because 0 is f of x vector, right? So you just have to check whether the bitwise complement entries are complementary or not, and this and this are complementary, 0 and 1, this and this are complementary, 0 and 1, this and this are complementary, 0 and 1, but this and this are not complementary. So therefore this function is not self-dual. Right? This property, if you find even one case where it's not complementary, it is not self-dual, right? So this is, so and similarly, yeah, so if f is not self-dual, then f bar is also not self-dual, right? That you can, it's easily you can easily see that from the property of the self-duality. So the f bar is not self-dual because f is not self-dual. So you cannot implement it in the mirror stack manner. So therefore, since there are 4 terms in the OR, you will have to implement it using a stack size of 4, right? In the Cmos, the number of OR terms is equal to the Cmos stack size because it is not a mirrorable function. If it was a mirrorable function, it would have been equal to the number of the NMOS stack size and Cmos stack size would have been equal. And in this case, you have 3 AND terms everywhere. So the NMOS stack size is 3. But yeah, unfortunately not self-dual. So yeah, the answer is 4. A logic gate is required whose inputs change at a constant frequency of 1 Hz. So most importantly, you can see that so the static CMOS, the skewed gate, and the CVSL are all actively holding their outputs at certain values for all possible inputs. But the dynamic CMOS, which for example is, let's say you take a unfooted dynamic inverter, right? The clock is an input, A is an input, The idea is that when clock is equal to 1 and A is equal to 0, the output is floating. So there exists a particular input combination, right, at which the output will float, and since the output is floating, it will obviously leak. It will leak through the N stack to ground because the NMOS is generally stronger than the PMOS in a dynamic Cmos gate, right? So you expect that the output will be 1, but it is now going to leak to 0. So therefore it is not functional. So this situation, if it stays on for a long time, which it will if the frequency is 1 Hertz, so this leakage will complete, right? It will cross the V IH of the next gate, right? Whatever gate this gate is driving, it will go below the VIH of that gate, and so therefore you lose functionality because the input frequency is so low. That is, the input time period is so large, right? So this is the only not correct option. So in question number 3, we are given an expression and we are asked to find the minimum PMOS stack size required to implement this in CMOS logic, with the addendum that you will have to reduce this expression to a form that minimizes the PMOS stack required, right? So let's look at it for question number 3. So in question number 3, this is the expression, and clearly you can see this is the expression and this is the reduction. It finally reduces to A into B into A and B and C and D the whole bar, which is just a 4-input NAND gate. And you can pause the video at this point to see the working of the reduction, right? But yeah, so a 4-input NAND gate requires only a PMOS of stack size 1. So that's the answer. In question number 4, an expression for F is this, and what is the minimum PMOS stack size required to implement this in CMOS logic, right? So we'll have to first perform the reduction to a form that minimizes the PMOS stack size, right? So this is the expression, and the claim is that we can replace that expression by the expression below, and the function is the exact same function. And let's look at why that is so. The idea is that, so this is the original expression and this is the replaced expression, right? So if A equal to 0, the original expression is, so if A equal to 0, then you'll get 0 plus BC, right? Because A bar will be 1, A bar will be 1, A will be 0. So first term becomes 0, second term just becomes BC, right? And similarly also in the replaced expression, if the first term becomes, so if A is 0, that goes to 0, and if if A is 0, then this goes, and this is 1, so it's just BC bar. So if A equal to 0, then both of them are equal, and if A equal to 1, now in the case of A equal to 1, you can do the same thing. You'll find that the original expression becomes this if A equal to 1, and the replaced expression also becomes this if A equal to 1. So if A equal to 0, they are equal. If A equal to 1, they are equal. So therefore the expressions must be equal. So now I replace this by this, and then I simply take this as common, right? So I've taken that as common. So we get A plus A bar, which is 1, right? And that becomes equal to this, the common term. And this you've seen is the carry out complement expression, which we've already shown in previous assignments is self-dual with a stack size of 2. And I'm sure sir would have also discussed this in class, that this is a self-dual function. And since I've shown you how to find out whether a function is self-dual in the question number 1, you can do the same thing for this expression. It's an expression of 3 variables, so you'll have actually a smaller truth table to deal with, and you can show that this is a self-dual function, so therefore you can mirror the n and p stacks, which means that the PMOS stack size required is 2, because you have all AND terms, two variable AND terms, which means the NMOS stack size is 2, and if you just mirror that on the PMOS, you'll get a PMOS stack size of 2, right? And so in question number 5, again, this is the expression for f given, and we'll have to reduce it to a form that minimizes the PMOS stack size. So that question number 4 is stack size of 2. You can see over here that now let's say you just distribute this product. So you will get a bar, then you will get a times that, then you will get, so a bar, a times that, and then you will get bc times a bar, and you will get bc times that, right? Now a bar goes to 0, and this is just a consensus theorem expression, right? So it's something like a into x plus a bar into y plus x into y. So this is x, you can take this as y, so this is x into y, right? So that is by consensus theorem just equal to ax plus a bar y, right? So that is now equal to this, and you can see this is the same expression as in question 4, the plus 0, you can ignore that plus 0, the or of 0, and yeah, so it's the same expression as question number 4, so it can be, it is just the carry out bar complement expression, and as you know, that requires a PMOS stack size of 2 because it's self-dual. In question 6, a Boolean function has the property that it has the self-dual property, and we are asked how many number of input combinations the output will be logic low for, right? So let's just think about this. So this is the self-dual property. Now consider a truth table of n variables. It will have 2 power n rows. Example, if there are 3 variables, then you'll have 8 rows in the truth table, 2 power 3, 8. Now half of those rows will be of the type f of x bar, and the other half will be of the type f of x bar complement. Take for example, this truth table. These are the input variables and this is the output, right? So you have half of them, that is 4 of them, of the form a0, a1, a2, a3, right? And the other half are of the form, this is a7 is a0 complement, a6 is a1 complement, you'll get a5 is a2 complement, and a4 is a3 complement. This is a3, right? So half of the rows are of the form, f of x bar for some x bar, and the x bar being x vector, f of x vector for some x vector, and the other half will be f of x vector bitwise complement, right? So this is f of a6, which is f of a1 complement, f of a7, which is f of a0 complement, like that, right? So now if you are saying that by the self-dual property, f of x complement is, f of x vector complement is f complement of x, that is the complement of this guy, then what you are saying is that whatever comes here will just be complemented here in the second half of the truth table, right? So that means that the number of logic zeros will have to be, so if there are n logic zeros here, if there are n zeros and m ones here, then there will be, every 0 here is a 1 here, so because it's complement, n ones and m zeros, right? So that means the total number of zeros will be n plus m, right? But we know that 2 times n plus m, that is the number of zeros here. So if you add the number of zeros here and the number of ones here and the number of ones here and the number of zeros here, you should get 2 power. Okay, so maybe n and m were bad variables. Let's say I choose C zeros and D ones. So you'll get C ones and D zeros. So the total number of zeros in the truth table outputs will be C zeros on the top plus D zeros on the bottom. But the total number of truth table entries is equal to C zeros on the top plus D ones on the top plus C ones on the bottom plus D ones on the bottom. And this is equal to 2 power n, as we've already discussed. So that means 2 times C plus D is 2 power n, which means C plus D is equal to 2 power n minus 1. And C plus D is the number of zeros. And so therefore the number of zeros then there must be 2 power n minus 1 number of x's for which f of x bar is equal to f of x vector is equal to 0. So that is the answer. So question number 7. What is the logical effort for rise in a pseudo NMOS 2-input NAND gate? So this is fairly straightforward, as would have been discussed in the class. Logical effort doesn't depend on the size. So let's just take a size 1 gate, right? So this is a pseudo NMOS 2-input NAND gate, and we are asked logical effort for rise. So you can assume that the inputs A and B are 0, right? So there's only the pull-up current, which is I by 3. And why is that I by 3? Because Pmos of size 2 pulls up a current of I. So you divide that by 3, 2 by 3. So the current will also get divided by 3 because the current is directly proportional to the width. Right? So it pulls up I by 3. So you'll have to take the reference inverter as one that pulls up I by 3. So this is 2 by 3. So therefore half of that is 1 by 3 equal rise and fall delay. So therefore you get the logical effort for rise is C gate by C ref, which is 8 by 3 divided by, so 8 by 3 is, what you see here, 8 by 3 divided by 2 by 3 plus 1 by 3. So that's 4 by 3. 2 by 3 plus 1 by 3 is 1. Sorry, so that's 8 by 3. Right? 2 by 3 plus 1 by 3 is 3 by 3. That's 1. So it's just 8 by 3. So that's the answer for the 7th question. And question number 8 is just similar to question number 7. It's logical effort for rise, except that we are asked for a pseudo NMOS 2-input NOR gate. If you work it out, it's very similar to the previous question. You will get the answer as 4 by 3. Right? So what is the logical effort for fall in a dynamic footed 3-input NOR gate for each input? Right? So this is a dynamic footed. So this has a footer, and it's a dynamic gate because there's a clock on each, on the header and the footer. And so therefore the stack size on the NMOS is 2. So I have taken 2 and 2 as the sizing. So now the pull down current is I, right? Pull down current is I, which means we have to compare it to the reference inverter, which has the same pull down current of I, right? So that gives us C gate of 3, and we have C reference of 3 and C gate of 2. So C gate by C reference, that's 2 by 3, right? And similarly, so 2 by 3 is the answer for question 9. In question number 10, what is the logical effort for fall in a dynamic unfooted 3-input NAND gate? So this is an unfooted 3-input NAND gate. There's no footer device. It's only a pull down stack. And it's a stack size of 3, so I've taken 3, 3, 3, and it pulls down a current of I. So similarly, this is the reference inverter. Reference inverter doesn't change, pulls down a current of I. So therefore C reference is 3, and C gate is also 3. So therefore G fall is C gate by C reference, which is 1. And so the answer is 1 for question 10. Now in question number 11, I will go over each and every option as to whether it is correct or not, or true or not. So the option A is false. Option A is false. Why? Because it's not true that pseudo NMOS inverter will be functional for all WP by WN. It only works for WP by WN such that the pull down network can overpower the pull up PMOS when the pull down network gets activated. So if it doesn't overpower the pull up PMOS, if the output voltage does not cross the VI, does not go below the VIH of the next gate, then the functionality is lost, right? Which is to say that, you know, if this is the PDN and this is the pull up PMOS tied to ground, and you know it's driving some gate, the idea is that when this stack is activated, it should pull the output below the, it should pull the output to 0, that is below the VIH of the next gate. But that will not always happen that is not going to happen for all possible WP by WN. For example, if the size WP is very, very large and WN is very, very small, then you know this output, it may just not cross, it may just not go below the VIH of the next gate. That is, it may not be registered as a logic 0. So therefore, it's not guaranteed that it will work for all WP and WN. That's why, you know, it's also called ratioed logic. It only works on certain ratios. Second option, dynamic circuit inputs are constrained to be monotonic, non-decreasing during the evaluate phase. Yes, because the idea is that let's say the input is 1, right, to a dynamic unfooted inverter. Let's say it doesn't matter whether it's footed or unfooted, I'm just giving an example. If the input is 1, the output gets pulled to 0, right? But then if the input now were to go to 0, there's nothing pulling it up again, because you know this during the evaluate phase phi is equal to 1, right? During the evaluate phase phi equal to 1, so the PMOS stack is off. So therefore the output is actually, so input is 0 and then the output is 0, so it's not a functional inverter, right? So yeah, the output has to be non-decreasing, right? So that is the, this is it has to be non-decreasing, so therefore this is true. And you know, this says it's the same sentence with non-increasing here, so this is false. Next we have option D, unfooted dynamic circuits are constrained to be 0 during the pre-charge phase. Yes, so again in an unfooted, during the pre-charge phase, that is the clock is equal to 0. Let's take an unfooted inverter for simplicity. So during 0, the output is now actively held at VDD. Now if A equal to 1, you will get a VDD ground short, and that's a bad thing. So therefore A has to be 0 to, it has to stay 0. It cannot go 1. So this is non-increasing, right? It has to stay 0 only, right? So that is yeah, so for one thing it's non-increasing, but it's actually constrained to be 0 only. So yeah, so the answer is constrained to be 0. And now in a footed dynamic circuit, this problem is not there because the footer will turn off the pull down stack, so the input can be whatever it wants to be, so it's not constrained to be 0. So this option is true, this option is false, right? In a footed gate, essentially the footer will turn off the, so even if A equal to 1, there is no contention of VDD ground, because so even if A is equal to 1, the footer will turn off the pull down stack, so it can only go till here. After that there's no path. So that's in a footed dynamic gate. A logic gate implemented in CVSL always has more transistors than the static CMOS implementation of the same gate, right? So that is true, right? So for option F, you will always have 2 extra cross coupled transistors in CVSL. That is, you will always have, let's say for example PMOS based CVSL, you'll always have this kind of the you know, cross coupled gates on the top. These are extra plus 2 transistors as greater than you know, CMOS. So therefore CVSL always has more number of transistors. So option F is also true. Dynamic circuit outputs are monotonic, non-increasing during the evaluate period. So the idea is that Let's again take the unfooted inverter as the example, right? So this is phi equal to 1 during the evaluate phase. Let's say A is equal to 0. That means the output stays high. If A were to suddenly become 1, output becomes 0. But now if A were to go to 0, the output, it will not go high because there's no pull-up path. So the idea is output can either stay a 1 or become a 0. It can never go from 0 to 1. So this is non-increasing. So that's the answer. Because it's a pull-down network which can never pull the output to VDD, it is a non-increasing output. Right? So this is true, and since this is the same sentence with non-decreasing, this is false. So those were the solutions to assignment 8.